Okay, today we are doing a question that is related to current carrying through a circular loop. So this kind of question is asked in an exam. So consider a circular loop of wire lying in a plane of a table. Let the current pass through the loop clockwise. Apply the right hand rule to find out the direction of the magnetic field inside and outside the loop. So we have to find the direction of magnetic field inside and outside the loop applying the right hand thumb rule, which you have studied before. Okay, now as you can see in the figure, the circuit is set up in such a way that the current is flowing in a clockwise direction in a circular loop. And if you place or your right hand pointing your thumb as per the clockwise direction, then you can find the direction of magnetic field by the curled fingers as shown in the figure, which is in the clockwise direction on the left hand side, and on the other side, if you place your right hand thumb in the similar way like before and find out the direction of the magnetic field here, you'll find the direction of magnetic field is anti-clockwise. So this is how we make a figure like this, and we find the direction of the magnetic field inside and outside the loop. So what do we find inside the loop? Inside the loop we find that the magnetic field seems to be merging inside the table, inside the loop, and outside the loop it seems that the magnetic field lines are coming out from the table outside the loop. Okay, this is the thing to understand in this question. Okay, next topic we will discuss is magnetic field and the number of turns of coil. So yeah, we have just studied that magnetic field produced in a circular loop, right? So if such circular loop are increased, if the number of turns of the circular loop are increased, suppose there are n turns of those circular loop, then what happens? The magnetic field of produced by that circular loop will also increase by n times. This is what we need to understand. So you can see here magnitude of the magnetic field gets sum up with increase in the number of turns of coil. If there are n turns of the coil, magnitude of magnetic field will be n times the magnetic field in case of single turn of coil. Okay, fine, I think it's clear. Now we are coming to a solenoid. So solenoid is actually a coil with many circular turns of insulated copper wire wrapped closely in the shape of cylinder. Here we can also add one more thing. The length of the solenoid must be greater than its diameter. Okay, that is also a very important point while defining about solenoid. What is that? The length of the solenoid must be greater than the diameter of the solenoid. So solenoid is simply a coil of many turns which is made up of insulated copper wire which is wrapped closely in the shape of cylinder. So a current carrying solenoid produce similar pattern of magnetic field. Now if we are coming to discuss about the pattern of magnetic field produced by a solenoid, then the pattern of the magnetic field produced by solenoid is similar to that of bar magnet. So one end of the solenoid behaves as a north pole and the other end behaves as a south pole, as you can see on the figure. Magnetic field lines are parallel inside the solenoid similar to the bar magnet, which shows that the magnetic field is same at all points inside the solenoid. Yes, that parallel lines inside the solenoid resembles or shows that the magnetic field is uniform inside the solenoid. And outside the solenoid, of course, we can see there is a spacing between the magnetic field lines. Hence, as we move away from the solenoid, the magnetic field or the magnetic strength decreases as we move away from the solenoid. Okay, by producing a strong magnetic field inside the solenoid, magnetic materials like soft iron can be magnetized by placing inside the coil. Yes, because there is a more amount, or there is a strong magnetic field produced inside the solenoid, and hence you can utilize that strong magnetic field to convert the magnetic material into a magnet. Such magnet is formed is called electromagnet. So I think electromagnet is clear to you. So how electromagnet is formed? Whenever a current is passed through a solenoid, and the solenoid consists of a soft iron core material, then that material can be magnetized, and hence formed is an electromagnet. Okay, you can see on the figure, your iron nail is turned, or iron nail is made. Here you can see that iron nail is turned out into an electromagnet by forming a solenoid. There are many number of turns of the copper wire, insulated copper wire, where the electric current is passed, and later this iron nail behaves as a magnet. Hence, it is an electromagnet. So, how to check the polarity of an electromagnet or a solenoid? So to check to check the polarity of the solenoid, what we can simply do is, one simple way is, we can bring a bar magnet near to one end of a solenoid, and suppose if we have brought a north pole of a bar magnet to one end of a solenoid, and suppose that bar magnet attract that solenoid, then it shows that those are the unlike poles. Suppose if you have brought north pole at one end of the solenoid, then if there is an attraction, it shows that that end of the solenoid is a south pole, and vice versa. Okay, this is the way how we can check the polarity of the solenoid. The other way of checking the polarity of the solenoid is simply you can apply the clock face rule, which we have studied just before. You can just see the circuit and find out whether the current is flowing clockwise or anti-clockwise in both of the ends. So yeah, in that way, if the current is flowing clockwise in one ends, then of course that is a south pole, and if the current is flowing in anti-clockwise in the other end, of course that is a north pole of the solenoid. Okay, fine, and this is all about solenoid. Now we get questions in exam in different forms. So there are some 3 marks questions I have segregated out here for today. So you can see, describe an activity to show that the magnetic field lines produced when current is passed through a circular coil. So we have already learned about the magnetic field produced in case of circular coil, but we have to describe it as an activity. So we will write its aim. The aim is to study the characteristics of magnetic field produced by current carrying circular coil simply. Okay, at its center is written here. Okay, we also are going to study at its center also, but right now simply we can just keep it to study the characteristics of magnetic field produced by a current carrying circular coil. So what are the apparatus required, materials required for conducting this activity? So we require a rectangular cardboard having 2 holes, thick copper circular coils of different radii having no number of turns, key, battery, rheostat, stand, iron fillings. Okay, these are the materials we require. And after that, the process we do is pass the coil through the 2 holes of the cardboard in such a way that the half of the loop is above the cardboard, and the remaining parts should be below it and the normal to the plane of the cardboard. Okay, so the wire should be perpendicularly placed on the cardboard as shown in the figure. Connect the circuit as shown. After connecting the circuit, sprinkle iron fillings uniformly on the cardboard. Allow the current to pass through the coil by inserting plug in the key. Note the pattern of iron fillings that emerges on the cardboard after tapping gently a few times. Okay, so we gently have to tap so that the iron fillings will get the respective shape of the magnetic field lines as shown in the figure. Place the compass at any point over the pattern of the field. Observe the direction of the needle. So we can, for finding out direction, we can simply use a magnetic compass and observe the direction. So observation, what do we find after doing this? Iron fillings are arranged in the form of concentric circles. The concentric circles becomes larger and larger as we move away from the wire. Okay, yes, as discussed in the theory. At the central of the loop, lines are almost straight and perpendicular to the plane of the loop. Okay, fine. So at the center, what we see is, we see the iron dust aligned perpendicularly to the plane of the loop. Okay, fine. So conclusion is the concentric circles at every point of the current carrying circular loop represent the magnetic field around it. Okay, yes. So we have already learned that in a circular current carrying loop, the magnetic field are in the form of concentric circles. So these concentric circles at every point of the current carrying circular loop represents the magnetic field around it. Magnetic field lines close to the axis of the loop is straight and perpendicular to the plane of the coil. Yes, so this is what we have studied. At the center of the circular loop, the magnetic field lines is straight. Field lines keep on diverging as we move away from the center of the loop. Okay, yes. So as we move from the center of the loop away, the field lines diverge. That means they are in the form of circle. So next question is in the form of solenoid. So already we have discussed about solenoid. Everything we have discussed. What is meant by solenoid? How does the current carrying solenoid behave? Yeah, so how it behaves, how the magnetic field lines are formed, it's mentioned here. And give its main use. Use of a solenoid is to make a temporary magnet, that is electromagnet, and as well as we can make permanent magnet using solenoid. Okay, fine. The next question is, for the current carrying solenoid as shown below, draw a magnetic field lines giving region. Explain that out of 3 points A, B and C, at which point the field strength is maximum and at which point it is minimum. So as we have already studied that the field lines are crowded more inside the solenoid, right? They are in the parallel fashion. So due to which the magnetic field lines, because it is more inside the solenoid, hence inside the solenoid the magnetic uh, strength is greater, magnetic field strength is greater. So outside the solenoid, of course, it is minimum, and at C it is intermediate of A and B. So I think it's clear. So inside the solenoid, that is A, magnetic field strength is maximum, and outside B it is minimum, and at C the field lines even at C is crowded. You can see in the figure just below, even at the position C you can see more number of magnetic field lines are crowded there. Hence magnetic field lines is in between A and B at position C.